We're really excited to share with you the work we've done this summer to try to improve our understanding of the complex physical processes occurring in the sun and how they create the so-called space weather events that can have a dramatic impact on our life here on Earth. When the sun emits high energy particles and electromagnetic radiation during the most powerful solar flares, it can harm electrical grids, satellites in orbit, and expose astronauts in space to potentially lethal doses of radiation. The earliest indicators of solar eruptions that lead to space weather events originate in the sun's magnetic field, especially through the emergence and evolution of so-called active regions, where the field becomes twisted or unstable. Therefore, it is important to build a model that forecasts the future state of the magnetic field to provide an early warning of solar activity before it turns into a hazard. To achieve this goal, we combine existing physics-based predictions with novel data-driven AI insights to build the most accurate and reliable forecasting of the emergence of active regions hours in advance and for the very first time. The spatial and temporal evolution of the solar magnetic field is currently predicted through sophisticated modeling of 2D surface magnetic flux transport, which is controlled by the physical processes of advective and turbulent transport, as well as the emergence of new regions of magnetic flux. To assist with this research, many space-based observatories, most notably the Solar Dynamics Observatory, have generated petabytes of multimodal data to probe the numerous physical processes underlying observed solar activity. However, too much of any good thing ultimately comes at a cost. At present, traditional statistical models struggle to handle this volume and complexity of data. Therefore, the field has moved towards the adoption of AI and machine learning to extract the full predictive power necessary for accurate and reliable space weather forecasting.
Now, I'd like to put the research part of heliophysics and AI in some historical context. As Nina mentioned, we've been sending out probes like SDO to study the sun for decades, and this has led to a massive influx of data. Concurrently, our abilities in large-scale data analysis have absolutely exploded, especially in the years since SDO launched. This has given rise to modern AI techniques like generative AI, transformers, and ResNets. Our most recent approaches to SFT modeling, AFT and ADAPT, both were initially developed around 2014, and we still consider these to be the state-of-the-art or SOTA today. However, these are well before the massive paradigm shift in scientific data analysis induced by AI. So we really haven't had the ability to address these long-standing challenges until now. Arcade explicitly addresses hurdles in accurate SFT modeling and modernizes active region forecasting for the AI age, while still taking advantage of existing knowledge in heliophysics. First of all, we incorporate multiple UQ techniques throughout our forecasting pipeline. We also cleanly integrate AI with existing mathematical models developed by heliophysicists. Finally, we establish successful short-term forecasts on the order of 6 hours in advance. Now, let's start getting into some more technical detail. We start by incorporating a wide range of solar data modalities, seen here. We then fit parameters in mathematical models to this data, as well as train neural networks to aid in numerical forecasts. And what this gives us is a deterministic forecasted magnetogram. And then, after prediction, these outputs are passed into another neural network, which returns Gaussian means and variances over the predicted magnetograms. This probabilistic perspective makes our results more interpretable and trustworthy to scientists and stakeholders. Altogether, this gives us what we want: data-driven, UQ-enabled magnetogram forecasts.
And as we design this workflow, we need to address the long-standing physics and AI divide. Because you know how physicists like to think in terms of equations that describe physical processes and in variables and parameters that can be empirically measured by instruments. Well, you see, deep learning models, on the other hand, can be huge and complex, and that sometimes makes them hard to interpret. So it stands to reason that these decades of petabytes of data stored in public repositories hold massive latent value if only AI models could scan them for patterns and do so in the language of physicists. And to do that, we created a model that takes in measurements of the solar surface as images and uses that to predict the future motion of active regions. The model solves the governing physics equations for surface flux transport using a ResNet. And the parameters that it learns through the model are used to create a future forecast. Here you can see what the input to the model looks like. It's a square image of the sun taken by instrumentation in space. And here you can see how the magnetic flux emergence is forecasted 6 hours into the future by our model. And you can compare it here with a full forecast from the target observation data. And here in the blue, lastly, you can see in the blue spots where uncertainty is quantified by the model. We call this arcade. And you can think of it as a real arcade where multiple systems come together, each bound by its own set of rules under a unified system to create a cohesive model of reality. This model is the first to marry AI and physics in this way. And it gives us interpretable equations, a cloud-native architecture, and a scalable framework that we can use to continue to advance on the state of the art.
Arcade, a novel approach that extends traditional SFT and physics-informed machine learning frameworks, as Plinio mentioned. For the first time, this enables uncertainty-aware forecasting of active regions. This capability opens new doors. With the development of high-resolution instruments and continuous solar monitoring, we have now access to vast volumes of high-quality data. For the first time, we can observe fine-scale structures and evolving patterns in active regions with unprecedented clarity of several solar cycle worth of data. By continuous integrating SDO observations and adapting flow fields using a combination of machine learning and space-based modeling, as shown in this demo, we move closer to operational forecasting and magnetic activity. It opens the door to predicting not just the transport of magnetic flux, but also the timing and location of new active region formation, which are key precursors of solar flares and CMEs. In short, Arcade approach represents a step forward in data-driven space weather modeling, one that blends physical realism, the adaptability and efficiency of AI, and uncertainty estimation to provide tools critical to both scientific research and practical forecasting. Arcade now enable us to understand and forecast the future of Sun, giving Earth an earlier warning that it had to prepare for change in the Sun. Finally, we would like to thank our sponsor, Google Cloud, for making this project possible, and the ARC team for making their simulation openly available. Thank you.